Let's talk about the logic of Anova. So why do we go through all these different variances, and most importantly, why is it called analysis of variance anyway? And this name, analysis of variance, does tend to lead to some confusion because we are going to be using variances, yes, but the main goal is to look at the differences between means of groups, right? I want to be able to compare the Beechnut, Del Monte, and Gerber groups on their means. So why are we talking about variance, and why is it called analysis of variance in the first place? So let's talk about the logic and how this all sort of pieces together. All right, so let's say I have my three means for Beechnut, Del Monte, and Gerber, and I can think about the grand mean here in the middle. So let's say we ignore the groups and we have these 15 babies, and I want to focus on just one particular baby. Let's just call it baby number 1. Doesn't matter which baby it is, I'm just giving it a name, okay? Baby number 1, let's say that this baby happens to be sort of far away from the grand mean. There's a certain distance. So we look at the grand mean is 6.333. This baby actually is some distance away. If I look at this as just one group, okay, just one single big group that has its variability. So the mean here is 6.333. This represents the grand, or the total variability between the 15 babies. And here's just our baby number 1 just sitting over here, okay? If I think about this distance, the distance from baby 1's score, this X here, and that grand mean, this is the amount of variability that baby number 1 contributes to the total variance. So that's the baby's distance from the grand mean, is the square distance from baby number 1 to the grand mean, right? So think baby number 1 minus the grand mean squared. I can do it for baby 2, baby 3, baby 4, baby 5, but I want to focus just on baby number 1. All right, so this is baby number 1's contribution to that grand, or that total variability between all the babies. All right, great. Baby number 1's not sort of by themselves. They're actually in a group. So we can start thinking about how baby number 1 looks relative to their own group. So here are the 3 groups and their variabilities, right? So the groups are differing from each other somewhat, but they have their own variabilities that we've seen, within groups variability. And this distance, this blue line here, is how far away that same baby number 1, is from their own group. All right, so go back a second. That's how far the baby number 1 is from the grand mean, right? So it's a much longer distance. This is how far baby number 1 is from their own group, right? That's the group mean that they're in right here. That's how far away they are from their own group, right? So this is the sum of each individual score from the group mean squared. So this is the distance that baby number 1 contributes to this equation. It's how far away that baby is from their own group mean, okay? Well, okay, so this baby is this far away from their group, and they're also got an even farther distance to the grand mean, but there's one more piece in there. So let's think about, look at the means and the variations of means around the grand mean. So these are the groups. So right now, if I'm looking at the groups, the group means from the grand mean, this is like the between groups sum of squares, I'm sort of ignoring the individual scores. But what is interesting is this mean for Beechnut, this mean right here, is the group that baby number 1 belongs to. And we can see how far that baby's group is from the grand mean. So this is how far baby number 1's group mean is from the grand mean. There's that distance there. So this is the contribution that first group, the Beechnut group, contributes to the overall differences between groups. So this is the distance from baby number 1's group to the grand mean. We would do this for baby number 1, and then also every baby in the beechnut group. So there are 5 babies in this same beechnut group. All 5 of those babies are going to have the same distance from their group mean to the grand mean. This is why we actually multiply by n. Because when we're looking at the group means, the group differences, the reason why is we are using the group mean to stand in for every baby that belongs to that group. So because we have 5 babies, I'm going to do it 5 times, but it's going to be the same number. The same group 1 mean minus the grand mean squared, and I'm going to do that 5 times. One's for each baby in the beechnut group. I'm going to do it 5 times. The same mean minus the grand mean 5 times for everybody in the Del Monte group. Same thing for everybody in the Gerber group. So I can do that, or I can do it once and multiply by 5, and that'll be the same thing. That's why we multiply by n here, is that it really represents the same distance for everybody that's in this group. Now, you might be thinking, well, that seems like a weird thing to do, but the reason why that is because the only thing that we know about the babies in the beechnut group is that they had the beechnut brand baby food. Okay, so we know that. We know that that makes them different than the babies in the Del Monte and the Gerber group. So I can explain, at least to a certain degree, why the means of these groups are different. Right? So it's the brand that they got that's actually making them either lower or higher in terms of the number of spoonfuls they ate. What I can't explain is the within groups variability. So why is baby number 1 different than other babies in the beechnut group? That I don't know. I know why the mean of the group is over here, because maybe beechnut is not liked as much as Del Monte or Gerber, but I don't know why baby number 1 and baby number 2, number 3, number 4, I don't know why their means are not closer together. There's something about those babies that are different that I can't explain. All I know is they all got the same food. They should have the same number, because they're all getting the same food, but they don't. They always have, there's going to be some variability, which we think of as sort of random noise or variability or something. But I can explain why this mean is different than that mean is different than that mean, because they got the different brands. That makes sense. So when we think about the total variability, let's go back a second. When we think about the total variability here, how far baby number 1 is away from the grand mean, I can actually think about this distance. I can break it up into 2 parts. The total variability between baby number 1, or the total distance between baby number 1 and the grand mean, can be cut up into how far is baby number 1 away from their own group, and then how far is their group away from the grand mean. So I can actually find the overall total distance for that baby away from the grand mean by looking at how far the baby is away from their own group, and then how far their group is away from the grand mean. So I can put this stuff all together. I can see that if you look at the red line again, the red line is the total variability between baby number 1 and the grand mean. And that distance can be cut up into, well, how far is that baby away from their own group, the blue line, and then how far is their group away from the grand mean, which is the green line. So that tells me that the sum of squares total, at least for this one baby, right, the distance, how much the baby is going to contribute to the variance, the sum of squares for that baby is going to equal, the total is going to equal to the sum of squares within their group plus the sum of squares between group. Right? So think about that. Baby number 1 from the grand mean, how far away they are from the grand mean, equals to how far baby number 1 is from his or her own group mean, and how far baby number 1's group mean is away from the grand mean. If you look at all babies at one time, remember all of them are contributing to the top of that variance equation, which we call the sum of squares, we can see that the sum of squares total equals to the sum of squares within groups plus the sum of squares between groups. We're able to take the total variability, how far each baby is away from the grand mean, and cut it up into, well, how much of that variability is due to differences between the groups, which is the part we can explain, or at least we think we can, because they got different brands of baby food, and some part of it that we can't explain, that is the within groups. It's sort of just the random variability between babies in the same group. It's the part we can't explain, right? They all got the same brand, but they didn't eat the same amount. So some babies may be hungrier, some of them may be just fussier, some may be teething, some may be whatever that's affecting how much they eat. And that we can't explain, but we can at least try to explain why the different brands led to different amounts of eating. All right, so the nice is we can take the total variability and break it up to the parts that's due to differences between groups and the part that is due to random variation within the groups. If we can do that, we can use this to our advantage and look at the between groups, which, even though it's a variability or it's a sum of squares, this is actually the part that we're most interested in. This is the part that has our, our group differences, right? So this has mean differences in it. Right? There are mean differences there. We're comparing each mean, instead of comparing them to each other, to other means of other groups, we're comparing all the groups to one grand mean. But the farther groups are apart, the farther they're going to be from the grand mean. So this is where our sort of hypothesis lies, right? In our between groups sum of squares, or between groups variance, is where our hypothesis, where the mean differences are coming from. So even though it's called analysis of variance, we're going to use the idea of variance to compare group means to one another indirectly. So instead of comparing, like in a t-test, we compare one group mean to another group mean. Here, we're going to compare all the group means to one grand mean with the idea the larger the variability is, the farther apart those means are, the bigger the mean differences are. So if I can use this difference in our sum of squares or between groups variance to our advantage to see if there's a significant difference between those group means. So we're basically using variance to ask the question about differences between the means by converting those mean differences into a variance. Okay. So what do we do with all that information and how does it work? Since we know that, since I just said that this within groups part is a part that we can't explain and we're going to sort of assume is sort of like error, we can use that to our advantage too and be able to figure out, well, how large is the between groups variation relative to within groups if we assume the within groups represents a sort of a random variability, a random noise. And we know we used that before. When we did the independent sample t-test, we got the pooled variance in order to find, to use that in our denominator to solve for t and to do a t-test. So we're going to do the same thing. We're going to pool the variances together to get a within groups variance. We're going to use that as our measure of random variability to see if our between groups variance is larger, large enough, larger than the within groups to have a significant difference. It's just going to require a slightly different distribution. Okay. So taking the sum of squares, we can create corresponding between groups, within groups, and total variances. So between groups represents average square deviations of groups from the grand mean. This is the part that's important, the part that we're actually interested in. It's the average difference between all the groups and the grand mean. If the variance there is very small, it tells me that the groups aren't very different from one another. The bigger that variance gets, the farther apart the groups are because they're getting farther and farther away from the grand mean. The within groups represents average individual scores from the group means that we're going to treat as error. That we're going to treat as sort of random variability, just like we did with t-tests. The pooled variance was something we used to estimate what's the random variability between people on average across these groups. We're just doing it for more groups. With t-tests, we were limited to just 2 groups, or here we can do 3, 4, 10, 12, 17, whatever, how many groups you want. And we're going to find the same pooled variance and use that as our measure of sort of random variability. All right. If groups are different, i.e. there is a between groups variance, this can be attributed to the different treatment of the groups. And this is sort of where this starts to come in. All right, well, if the brands were really that different, if babies, responded differently to the brands, then if babies eat more peas from some brands and less from others, we can attribute this to the brands they were assigned to, and that would have a larger between groups variance. Right. However, the different treatments, brands, for example, do not explain why babies within the same groups didn't eat the same amount. They got the same treatment, they get the same, the same brand, but yet they ate different amounts. So variation within each group is therefore considered random. It's just random error variance. It's unexplainable random variance. Now, it may not be completely random, but we're going to, for the sake of the test for the Anova, assume that it's random and sort of use it that way. Okay. All right, so remembering that the mean square within groups is the same thing as the variance within groups, contains the random sampling variation among the participants. So it's just random noise that we can't explain between the babies eating, amount of food they ate. The mean square between groups also contains random variations, like random sampling variation, because if we were to redistribute the babies out, like randomly assign them in different ways, we might get different variation. Means might change depending on how the babies were randomly assigned. So there's a bit of random variation there too, but it also contains, importantly, they call it the systematic, but just think of it as the sort of real differences as well, right? So if there's real differences that are due to the brands, that also occurs in between groups. The brands actually pushing the babies farther apart. So the between groups has both. Within groups only has error, random noise. Between groups has both real variation that occurs because of the brand in this case, and it also has some random sampling variation too. So the thing we want to do is be able to get this real part alone. I want to be able to isolate the amount of real variation between the groups. So because they're both variances, and they both, at least in part, contain a measure of random variation, I can divide them. If I take the mean square between groups, which contains both real variation and random sampling variation, has both real and random, and the mean square within groups is a measure of random, well, I can actually isolate the real variation by dividing them so that the random variation here and the random variation here essentially cancel each other out, right? And what you're left with is the real variation between the groups. And we can test that for significance. We can test it using this distribution, the F distribution. So for analysis of variance, we're going to use the F distribution because it is specifically designed to look at the ratio of variances like this between groups over within groups and look at whether or not that is a significant ratio. So that's the distribution we're going to switch to. So we started with Z, we went to a T distribution, now we're moving to an F distribution. And F is particular for looking at the ratios of variances. So the F test is a ratio, the mean square between over within, we just said. And if the group differences are just random, so let's say that we give the babies these different brands, and they really don't differ that much. The differences between the groups is just random. So you get random between groups variance over random within groups variance. They're going to be about the same size, random between, random within. So when you divide them, you're going to get a number about 1. So an F value of 1 really indicates that there's really no group differences, at least not substantial ones. So if there aren't really any real differences between the groups, we'd expect to get an F ratio of about 1, roughly equal to 1 someplace, right? Because the means are just sort of on top of one another. They're not very different around the grand mean. As those differences get larger, right, the means start to spread apart, and then you're now starting to see them vary away from the grand mean like this. If there are real differences between the groups, the F ratio will be larger than 1. The farther apart the groups are, the bigger the F ratio is going to get. It's going to get more and more positive. It's going to move farther and farther away from 1. So we need to calculate the probability. Well, how far away from 1 do we have to be for it to be sort of significant? You need to be able to figure out what the distribution looks like, find an alpha, a 0.05 region for rejection, and be able to test that. So we do that using an F distribution, which looks like this. So F distributions look markedly different than our Z and T distributions that were normally distributed. Right? So a Z and T essentially center at 0 and are like a bell-shaped curve, right? So this is what we're typically used to with Z and T distributions. This looks very different. Notice that the center, well, not really the center, but the peak is at 1. That's that, because if you have just basically random over random, we'd expect it to be 1. So that's where that is. And then because they're variances, and variances are positive, you're always taking a positive variance dividing by another positive variance. You're not going to have any negative numbers. Right? You don't have negative variances, so there's no negative numbers. So an F distribution is completely positive, and because of that, it is this sort of right or positively skewed distribution. Right? So where it has a very short tail on one end, and then a very long tail going in the positive direction. But it does allow us to figure out, okay, well, where's the alpha region and how far above, what number do we have to be above in order to figure out if we're significant or not. There is a separate F distribution for every degrees of freedom, like T, right? So T had a different table for every degrees of freedom. The difference here is that you actually need both degrees of freedom for an F test. You need both the between groups degrees of freedom and the within groups degrees of freedom to figure out the F critical value from the F table. And the ones that are available to you, like on Canvas, the F table, there's just 2 F tables. There's one for alpha equals 0.05 and a separate one for alpha equals 0.01. Right, so there's just 2 F tables. You're going to use your between groups and within groups degrees of freedom to then look up those numbers. Let's take a quick look at that. Let me erase this for a second. All right, so here's our T distribution. And scroll down, here's F. Okay, so this is the 0.05 one, which is the one you're going to use likely a lot more often. So across the top are the degrees of freedom between. So think about our example. We had 3 groups. So our degrees of freedom between are going to be 3 minus 1 is 2, k minus 1. So 3 minus 1 equals 2. 2 degrees of freedom. All right, so we're going to start this column. That's what it says. Along the side are degrees of freedom for the denominator, the degrees of freedom within. So within groups is going to be the total number of subjects, which is capital N, big N, minus the number of groups. So I have 15 babies minus 3 groups is 12. So I'm going to go down this 2 column to the 12 row, and I'm going to find this 3.885 number, let me make it a little bigger, which is my F critical value at alpha equals 0.05 with 2 and 12 degrees of freedom. That's how this works. You find the between groups degrees of freedom across the top, within groups degrees of freedom along the side, and you find where those two meet, and that is your critical value. Alright, so let's go back to the example. So we've actually already done all the work that we need to do. We actually have all the information, but let's just go through it, once again, just go through it. Now that we sort of know what we know, and we've talked a little bit about the logic, let's sort of walk through it again, just to make sure that we're all clear and know sort of what to do. So let's put it all together and get to a conclusion. So back to the example, we have our Bisneta Monte Gerber babies eating the 3 different brands of strain peas. We have their means, innovations, variances across all the different groups. So now we have all the tools to actually go through and do this like 7 hypothesis testing steps and be able to come to a conclusion about, do babies really prefer the brands differently? So even though in some ways analysis of variance is a little bit more complicated than, say, a t-test or something, one of the nice things about Anova is it's considered an omnibus test. Omnibus, so it's a funny word, but which means that the idea of thinking about one-tailed versus two-tailed tests So that goes out the window. It's unlike, t-tests where you have to decide if it's one-tailed or two-tailed and that stuff. Anovas are considered sort of like a no-tailed test. Even though the F distribution has a single tail, it's comparing all the groups to each other, and it's looking for any differences. So it's not looking for differences, in one direction or another. It's looking for anything. So it's actually more similar in that way to a two-tailed test, because it's just looking for any differences. But in a way, it's just a no-tailed test. There's no direction. It's not, we're not looking at it that way. All right, so the null and alternative hypotheses are going to look the same most of the time. The null is that all the groups are equal. There's no differences. Okay. The alternative is, well, at least two of the means are different. Now you could say this different ways. At least one mean is different than others, or something like that. All it takes is for two of the groups to be different for you to be able to reject the null hypothesis. So the null is they're all equal. The alternative is not that they're not all equal, because it doesn't mean that they have to all be different. Right? You can have 5 groups where 4 of them are exactly the same and one mean is different, and it might reject the null. So all it takes is for 2 means to be different, and you might reject that null hypothesis. We're going to still assume alpha is 0.05. That hasn't changed. Because we have more than 2 groups, we know this is Anova, and we're doing an F test using an F distribution. For F critical value, you need both degrees of freedom between groups, which we figured out again was the number of groups. K minus 1 is 2. And degrees of freedom within groups, which is the total number of subjects, in this case 15 babies, minus the number of groups, which is in this case is 3 groups. So 15 minus 3 is 12. So as we just did, table F, go to the F table, and we're going to look up F critical with 2 and 12. And we found it was 3.89. Let's do that again just real quick, because it doesn't hurt. Here's my F with 2 degrees of freedom. We're going to go down to 12 degrees of freedom, and we get 3.885, which I simply rounded up in the slide to 3.89, but the same thing. 3.885 or 3.89 is our critical value with 2 and 12 degrees of freedom. Our decision rule then is if my F observed now, I remember we used T observed before, but now we're going to compute an F observed. If my F observed is larger than my critical value, 3.89, I'm going to reject the null hypothesis. That's my decision rule. And just like with the independent samples t-test, the main, the part of Anova you can spend the most time on is step 6, because now there's going to be some multiple steps to sort of find the F observed value. So to calculate an F test, you're going to start, the way this is done is to sort of create what's called an Anova summary table. And we'll get to that in a second. But to find an Anova summary table, you're going to start off with finding the sum of squares. You're then going to find the degrees of freedom. You're then going to use the 2 of those to figure out the between groups and within groups variances, the mean square between and mean square within. And then you're going to use that to find F. All right? Sum of squares, degrees of freedom, mean square, F. That's the sort of process. So we're going to start computing the sum of squares first. Again, we already did this earlier in this section, this lecture, one of the earlier parts of this Anova lecture. But let's sort of run through it again, just to make sure we're all on the same page, and it may make more sense now what it is we're doing and why we're doing it. So there are 3 sums of squares we're going to look for. We need to compute the total sum of squares, which is the differences between each score in each group around the grand mean. Okay. And you might notice that here all of a sudden there are y's instead of x's. That shouldn't matter, right? So whether I'm calling it the outcomes y or x or z or whatever it is, shouldn't make a difference. It's just these are the individual scores on some variable I'm calling y, minus the grand mean of that on that variable. Squaring each time is my total, so each score around the grand mean. Down here within groups is each score around its own group right, which is the within groups. And then I have the groups around the grand mean. And this is one that telltale sign of the between groups is always that there's an n in there somewhere. The only one that has an n being multiplied is my then between group sum of squares, where the total sum of squares equals the between groups plus the within groups, or shorthand SST equals sum of squares between groups equals sum of squares, or sorry, plus sum of squares within groups. I'll say it again. Sum of squares T equals sum of squares BG plus sum of squares WG. And just for the sake of completeness, you may also see in other places these referred to as sum of squares T for total still equals the sum of squares for the effect plus the sum of squares for error. And it's because the effect that we're talking about here, like the effect would be the effect of brand. So what's the sum of squares for the effect? And because the effect was randomly assigned to different groups, effect and between group are the same thing. And so just another word for effect. And I mentioned before that we treat or consider the differences within each group to be sort of random variability or random error. So the term error, I know, is sort of a weird one because we have a connotation about being a mistake or something, but error in this case is just the unexplained variation, right? Unexplained variance. So that means that within groups and error also mean the same thing. So if you see, effect plus error, that's just a different way of writing between groups plus within groups when we're talking about Anova. All right, so let's think about this again. So here is I now need to get a sum of squares total. Now I have that it's 71.333 just here, just to make sure that we know what it is, but let's again figure out, we did this before, but I think it's worth sort of doing again just for the sake of completeness and thoroughness and make sure that we're all on the same page. How do I get each individual minus the grand mean? All right, there's only one grand mean, which is 6.333. All right, so it's going to be 3 minus 6.333 squared plus, I have 4 the last one's 8. Okay. I'm going to keep going. Boop, boop. The next one. So now I have 7, 4, 8, 6, 5, 9, 6, 10, 8, 9. That. All minus 6.333 squared. Keep on subtracting. All right, so if we subtract, and we actually did it before, so if we actually go back to an earlier part of the lecture, you can sort of see it. But if we actually subtract and square each one of these, add them all up, we'll get that 71.333. In fact, let's just do it again, because why not? Let's make sure we're all on the same page. So it's 3 minus 6.333. 3 minus 6.333 equals negative 3.333. And I'm going to square that. So this is 11. Yeah, I'll do it in a different marker color. So this is now 11.109. Okay. And so you have threes. Nope. So 4 minus 6.333 equals negative 2.333 squared, 5.443. Okay. Let's keep on going. Once this is 5.443, 5.443. This is also 5.443. That's it. So let's do 8 minus 6.333 equals 8 minus 6.333 equals 1.667 squared, 2.779. 2.779. The other 8s. So here's 2.779. 2.779. All right, let's do 6. 6 minus 6.333 is negative 0.333 squared, 0.111. So this is 0.111. This is 0.111. All right, let's do 7. 7 minus 6.333 equals 0.667 squared is 0.445. The other 7s, nope. 5 minus 6.333 equals negative 1.333 squared is 1.777. 1.777. And there's only 5, I think. So let's do 9. 9 minus 6.333 equals 2.667. Squared is 7.113. 7.113. 7.113. And then this last one, 10 minus 6.333 equals 3.667 squared, 13.447. All right, now let's add it up and see if we do get this number. All right. 11.109 plus 5.443 plus 5.443 plus 5.443 plus 2.779 plus 0.445. I put 0.44 without a 5, but whatever, it'll be a little off of the whatever. 5.443 plus 2.779 plus 0.111 plus 1.777 plus 7.113 plus 0.111 plus 13.447 plus 2.779 plus 7.113 equals, so I get 71.33, which is 71.33 is pretty close. The only thing I was missing was like plus a 0.005, so I get 71.335 instead. If I had got this number there correct, but it's still really, really close. All right, so that we're basically getting the same number, adding up all of these square deviations around the grand mean. So giving us a total sums of squares. All right, what's the first one? That's the sum of squares total. So let's go on and find the other two sum of squares. Only one of them is sort of tedious like this. The other one's actually a lot easier. Sum of squares total equals 71.333. Okay, let's put that there, just in case. And then, so now we know, it's telling me here that the sum of squares within groups should be 34.4. So let's figure out how I found that. So this one looks, again, it has a similar setup in that we're doing it for every single score, but instead we're going to subtract out the group mean instead of the grand mean. So it's going to be the same thing as like, so I'll do it down here again. 3, 4, 4, 4, and 8. Right? 3, 4, 4, 4, 8. And then 7, 4, 8, 6, 5. 7, 4, 8, 6, 5. And then 9, 6, 10, 8, 9. 6, 10, 8, 9. So across the first row, I'm subtracting 4.6. 4.6. Minus 4.6. Minus 4.6. All the way for group 1. I'm going to keep going. For group 2, I get to transition over to the next group mean. So 6. So 7 minus 6 squared plus 4 minus 6 plus 8 minus 6 squared, 6 minus 6 squared plus 5 minus 6 squared. Now I'm going to keep going. Go to the other group. 8.4. 9 minus 8.4 squared. 6 minus 8.4 squared. Minus 8.4 squared. 8 minus 8.4 squared plus 9 minus 8.4 squared equals squared. Let's go through and figure out all those. Alright, so 3 minus 4.6 equals negative 1.6. Squared is 2.56. What's that one? So 4 minus 4.6 is negative 0.6 squared. This is 0.36. 0.36. 0.36. Okay. And then 8 minus 4.6 equals 3.4 squared is 11.56. Okay. And then 7 minus 6 is 1. 1 squared is 1. This is going to be 4. 8 minus 6 is 2 squared is 4. This is 0. 1 minus 6 is negative 1. Squared is still 1. 9 minus 8.4 equals 0.6. 0.6 squared is 30.36. 6 minus 8.4 is negative 2.4. Squared is 5.76. 10 minus 8.4 equals 1.6. 1.6 squared is 2.56. 8 minus 8.4 equals 0.4. Squared is 0.16. 9 minus 8.4 equals 0.6. Squared is 0.36. Okay. Let's add them all up. 2.56 plus 0.36 plus 0.36 plus 0.36 plus 11.56 plus 1 plus 4 plus 4 plus 0 plus 1 plus 0.36 plus 5.76 plus 2.56 plus 0.16 plus 0.36 equals 34.4. Yay! Okay, that looks exactly the same as that. Okay. Okay. So that works out. Right, so it's just taking deviations of scores around their own group means, adding them up, and I get 34.4 is my answer. So I'm going to write that up here as well. So sum of squares within groups equals 34.4. Alright, so for the sort of main attraction, the thing that we're most interested in, which is the sum of squares between groups, it's actually a much easier time. You got mean of each group minus the grand mean squared multiplied by n each time. All right, it's not too bad. So that is, first mean is 4.6 minus our 6.333 squared. And I'm going to multiply that by 5. So 5 times that number. All right, so that's the first one. I'm going to add to that 5 times the next one. 6 minus 6.333 squared. I'm going to add then 5 times the last one, 8.4. Square that. Okay. That's it. Let's see what I get. Alright, so 4.6 minus 6.333 equals, alright, so that's negative 1.733. I'm going to square it. It's 3.003 times 5 equals 15.016. So this is 15.016. 6 minus 6.333 equals negative 0.333 squared is 0.111 times 5 equals 0.554. Wait, oh, I see what's happening. 0.111 times, well, whatever. Let's do it. 6.333. 6 minus 6.333, is that squared is roughly 0.110889, which I think before we had rounded up to 0.111. If I multiply this times 15, 6 minus 6.333 equals squared times 5 equals 0.554445. All right, so this thing is this whole thing is 0.554, which I think before we had come up with 0.555 because of the rounding in between. 8.4 minus 6.333 equals 2.067 squared is 4.272489 times 5 equals 21.362. Okay, so 15.016 plus 0.554 plus 21.362. Ah, crap. 15.016 plus 0.554 plus 21.362 equals 36.932, which, I mean, that's super close to that, right? Just one value off in the third decimal. It's not too bad. All right, so I was able to do that, and again, I could have found the square differences of each one, added them up, and then multiplied by 5 because they're all the same. But in this case, I just did it. I followed the equation to do it that way. So up here, just as we the sum of squares between groups equals 36.93. I'll just leave this version up here, 0.933. Okay. All right, so checking our math, we can see if I take 34.4 and add that to 36.933, it equals 71.333. So When we say that the sum of squares total is equal to the sum of squares between plus sum of squares within, technically that should actually add up. This is one thing that is good to do if you're doing this for a quiz or an exam or something, is that when you find the sum of squares total between and within, you should then add them up to see if they all sort of add up right. If they do, then you feel at least safer that you did it sort of correctly. If you add up the between and within and it doesn't equal the total, then it tells you there's you probably got to go back and find out why something went wrong, and it might help you sort of fix the problem. Okay. Moving forward. So now what? We already talked about degrees of freedom, but let's sort of talk about them again. So we know that when we talk about big N, right, that large N, capital N equals all of the little n's added up. Right? So we have three groups, so I'm going to add them all up. So we say like big N minus 1, we have 15 babies. This is going to be 15 minus 1 equals 14 degrees of freedom. We have K is our number of groups, so we have 3 groups. So this is going to equal to 3 minus 1 equals 2. And then just plug these in here, which is N again is 15 minus 3 groups equals 12. All right, so we have all those degrees of freedom. All right. So now we need to combine our sum of squares and our degrees of freedom together to sort of compute the mean squares, or the variance between, the variance within, the variance total. All right, you actually don't have to really compute the variance total, but you can if you want. All right, so putting this together, we need to find a mean squared total. Again, this part you don't actually have to do, but you can. Mean square total, mean square between groups, mean square within groups. So how do we do that? Well, we take the sum of squares we already found, sum of squares total, sum of squares within and between, and you're going to divide each of those by the corresponding degrees of freedom. It's going to then you're basically converting them over from sum of squares to mean squares, or to variances. Okay, so we can do that. You can do that in these equations, but what typically happens, or what we usually do with an Anova, like the step 6, the outcome, the observed value, usually is computed as part of this thing called an Anova summary table. So what we do is we fill in all the parts. So we know our between group sum of squares. I wrote them up there just to make sure. Our between group sum of squares is 36.933. All right. 36.933. Okay. Our within groups is 34.4. Our total is 71.333. We already checked that these two add up to that, so that's good. Our degrees of freedom we figured out for between was 3 minus 1 equals 2. For within, it was 15 minus 3 equals 12. And for total, it was the total n, 15 minus 1, which is 14. You should also notice that these two should add up to that as well. So the degrees of freedom between, degrees of freedom within should add up to the total degrees of freedom. So now what? So now we have this first part together. If I take and divide this way, right? So I take 36.933 divided by 2 and 34.4 divided by 12, I can get the mean square between and mean square within. So 36.933 divided by 2 equals 18.467. All right, so 18.467. And I take my 34.4, divide that by 12, I get 2.867, which we found is our pooled variance from before. 2.867. Okay. Now you can take 71.333. Right? You can take that, divide it by 14 and get a value here, but we're not going to do anything with it. It's just going to sit there. So it's not really necessary to compute. It can, we don't need to. Because what we really need to do now is just to figure out, to get my f value, I'm now going to divide the other way. I'm going to take and divide, I guess pink, this way. Whoop. I'm going to take 18.467, divide that by 2.867, and that's going to give me my f value. And remember, my f ratio is my mean square between over my mean square within, so I can just divide those two. 18.467 divided by 2.867 equals 6.441. So this is going to be 6.441. And that is my f value. I can go back to my decision rule now and say, all right, step 7, since 6.441 is greater than 3.89, we're going to reject the null hypothesis. So what was a null? The null said that all the groups are equal. So all means are equal. So we're rejecting that. So we know that not all means are equal. So there's at least one mean or two means that are different from each other in order for us to be able to reject the null hypothesis. They don't have to all be different, but there has to be at least two of them that are significantly different from each other for us to reject the null hypothesis here. All right, and that takes us all the way through steps 6 and 7 to making our conclusion. And it seems like it's a pain in the butt. It is. There's a lot of extra steps, but because of the steps of it and how it's sort of laid out, and even putting it together in this nice table, lots of students will find that this makes more sense, and they actually will have an easier time sort of going through Anova than they did even with independent samples t-tests. Because even though it's more steps, they seem a lot more laid out, and you know, students have sometimes an easier time sort of following those steps because of how nicely it is laid out in these sort of tables and things. Right, so that's how to do the test. But one thing I want you to want to point out here is that, again, we found out that not all groups were equal, right? So we know that we can reject the null, which states that all groups are equal. All right, great. So that means that there's some difference there or some differences there, but I don't know where. All right, so the Anova tells me that there are differences. Differences exist between the groups in my my test and my analysis, but they don't tell me where. And that's problematic. So go back to the example that we're talking about. It's supposed to be a market research, and I want to know which brand babies prefer the most. Well, all this Anova does is tell me that the babies prefer them differently, but it doesn't really tell me which one is significantly better or worse. Even though we've done this sort of complicated step-by-step thing, all we really know is that there are some differences, but there's still some more work to do. So this is like step number 1. It tells you, yes, there are differences here, but you're going to need to do a little bit more work to find them. So the Anova really is just, again, it's an omnibus sort of global test to tell you with 1.05 alpha level if differences exist between your groups, but it just doesn't tell you where they are. So how do we find out where they are? Well, that's the next part. The F for groups here is significant. So a couple different ways of seeing this is we would obtain an F of this size when the null is true less than 5% of the time. All right, so if the null actually was true and the means were all equal, we would get an F value of this size less than 5% of the time. So random differences between the groups is not a very likely answer, very explanation for the value that we got. So a better explanation is that the babies prefer the brands differently, right? The difference in group means cannot be explained by random error. So the baby food brands were rated differently by the sample of babies. But again, it's different. We don't know which, but we do know that there is some difference. The rating did matter, okay? Or the brands did matter in terms of rating. We don't know exactly how yet. we just know in this first level, this first, you know, at the global sort of Anova test, that there is some differences and we should proceed forward to find them. All right, so what happens if you have unequal sample sizes? I sort of mentioned this before. With one way, it's not a particular problem. Like if you have a one-way Anova that, like we're talking about, it's not really an issue. It doesn't really do much. You can multiply mean deviations by appropriate, it's supposed to be n sub j, it looks like an I, but the appropriate n sub j as you go. The problem is more complex with more complex designs. So as we get into like factorial and repeated measures designs, they become a little bit more of a problem here. But equal samples only simplify the equation. I mentioned before, because when n1 equals n2, all the n's are equal. You can actually factor, because you're doing this each time, this n sub j, you know, multiplying each of the deviations, you can actually factor that out and actually just have one n at the end. So you can sum all the deviations up, the square deviations up, and multiply by n once. So it does simplify things if the n's are equal. But when they're not equal, it doesn't really affect things. It just means that you're having to multiply by the different n each time you do a deviation, which, you know, is maybe more tedious, but it doesn't change much of anything.